Good evening and welcome to the Chaos West stage. The next talk is about storing energy in the 21st century. Frank is a journalist mostly writing on manned spaceflight, but also working on energy storage. And he's going to tell us what his ideas are, what his knowledge about solutions for the future of storing energy will be. Please welcome him.
Hi. As was already said, I'm a journalist and I'm a podcaster. I write text. I speak into microphones. Doing presentations is not part of my job. My presentations are bad. I'm sorry about that. So this talk is going to be about energy storage in 21st century. If you expect this to be about the future, you're only half right. Because if you had a look at the calendar, it's 2020. We are in the 21st century. And one of the things we need to talk about is our state right now and how we got here. And you might be a bit surprised by my first slide. Yeah, 1859, lead-acid batteries. Actually, the very first kind of battery that was ever invented that was actually rechargeable. And it's still the most popular battery around. As you can see, it's over 370 gigawatt hours of lead-acid batteries are produced every year to date. And that's more than twice, or maybe this year it's just about twice of what we have in production in lithium-ion batteries. So this is really still a very important technology. And yeah, electric cars are not very modern invention. In fact, around the start of last century, they were quite popular. And lots of people will say, yeah, okay, this was the moment when everything went bad. But if you look at the actual performance of these cars, well, this was for early adopters. They had 4 horsepower, 3 kilowatts of power. They were driving at about the speed of what you would walk, maybe a little bit faster. And if you were trying to go up a hill, this thing still weighs a ton. I mean, it's almost as heavy as a modern car. They were not very good overall. When you have a real car, you need a bit more than that. These days, about 70 million passenger cars are produced every year. 25 million commercial vehicles like vans, trucks, tractors, and so on are produced every year. And about 90 kilowatt hours of lithium-ion batteries are put into electric cars. So if we took all the production of passenger cars and divided the batteries among them, it's 1.5 kilowatt hours per car. That's not quite enough. So the number of electric vehicles you see on the street is not because people are not willing to make more, but they just don't have enough batteries for that. We need at least 3,500 gigawatt hours, and that's about 20 times the current production of lithium-ion batteries, just to supply passenger cars. All the other things like trucks, vans, vehicles, maybe grid storage, all the other things that you need the lithium-ion batteries for is not included in that figure. But in fact, lithium-ion batteries are still fairly modern technology, and there were others, like nickel-cadmium, also at the turn of the century, and yet others like nickel-iron. And what happened with nickel-iron is that they replaced the cadmium with iron. In fact, it was still a bit more expensive to produce, but these batteries kind of worked. And that was a great advantage. On the other hand, nobody quite knew why they worked. In fact, when you see the formulas here, these formulas were figured out in around 1960 or so. Before that, it was very hard to figure this out because you couldn't actually look into the battery and do all the chemical analysis, and they needed near-infrared spectrometry to figure that out. Now, if you look at that formula and you squint a bit and maybe subtract the OH here from the H2O, what you actually see is that here's the hydrogen and it moves over to the nickel. And this was something that was observed, and somebody had the idea that you could just build a battery without any cadmium or any iron. You just have hydrogen in there. And these batteries were actually quite successful, even though you might never have heard of them, because they were mostly used in space. Hubble Space Telescope still has them. The International Space Station had them or has them. They're currently being replaced by lithium batteries. But they were quite important, at least in that area, especially because they had they could sustain a large number of cycles, like 20,000, 50,000. And you have to remember, they were used in satellites or like the space station in very low orbits. So every 90 minutes, they go once around the Earth, and they have a sunrise and a sunset every 90 minutes. So about 6,000 per year. And so you get 6,000 cycles every year. And your battery has to be able to sustain that. However, these batteries were absolutely not suitable for anything here on Earth. For one thing, you don't really want to have a pressure vessel filled with anything around you, because it's really high pressure and something might go wrong, especially when you build like millions of them. And also inside there is gas. There's actually hydrogen being developed inside the battery. And as soon as it leaks, the hydrogen is out there. It's flammable. It's possibly explosive. You don't really want that. So people had a better idea. Actually, they had this idea before. They said, well, we can just use the hydrogen gas. And they stored the hydrogen in the form of hydrides. And you all have these batteries. They're the typical AEA rechargeable batteries with 1.2 volts. And they're chemically exactly the same. They're chemically exactly the same thing, because they make hydrogen, and the hydrogen gets stored inside this black stuff here, and the black stuff is a metal, a mixture of metals that easily forms hydrides. And so you have a chemical bond, but a very easy chemical bond between the hydrogen and the material inside there. So the material can take up the hydrogen and give it off, even at room temperature, at fairly good rates, at least good enough for the batteries. The problem is it's pretty darn heavy. When you look at like the stuff that's in there, it's mostly nickel and cobalt and a bit of lanthanide, and that was the first mixture. These days there are others that are a little bit better and completely different materials like titanium, but almost always some nickel. And yeah, there were others. Ford patented this one, actually for cars. Yes, Ford did want to build electric cars, and the battery they had was almost as good as lithium-ion batteries around 1990. They were quite good. They were about 3 times as good as lead-acid batteries. Only problem is it's a high-temperature battery. Sodium and the sulfur are both liquid. And if you ever had sodium somewhere if you've ever seen the experiment in chemistry where sodium was in water and it exploded, well, if the sodium is liquid, it gets worse. It gets much worse. And in this battery, the sodium and the sulfur are divided by a solid electrolyte. And the solid electrolyte is actually a kind of ceramic. It's aluminum oxide. It's fairly brittle and porous. It has to be porous because something has to get through. So the sodium and sulfur can react with each other. And no, you cannot really use this stuff in a car, which is kind of obvious. You don't want to have liquid sodium in your car. And these batteries are actually still used these days in grid storage, especially in Japan. There's a company I had never heard of when I read about those in 2010. And I know it's 2010 because that company was TEPCO, if anybody remembers this, and why this is why it's so important that I read about this in 2010 and remember this sometime later in 2011. But the problem is a lot of these batteries, and we'll talk about lithium-ion batteries in a moment. Materials. This is one of my favorite charts in Wikipedia. It's the abundance of chemical elements in the Earth's continental crust. It's a bit of a lie. We have oceans, and the oceans contain a lot less hydrogen than would be in this table. This is not a complete table. I took some sections out just to show some important bits here. Like, lead is down here, it's fairly rare. Lithium is also quite rare. The reason lithium is rare is because of what happens in the sun. Lithium is very susceptible to nuclear fusion. So in nuclear fusion, lithium almost immediately gets burned, and we don't have a lot of lithium anywhere in the universe. Also not on Earth, as you can see. Cobalt is almost the same. And actually, if you want to build batteries, and you want to build a lot of batteries, you want to have something rather up there, as far up as possible. Like, sodium, for example. We had sodium-sulfur batteries. Sulfur would be somewhere in between here. But we have a lot of sulfur because, in case you didn't know, we do produce a lot of oil. And there's a lot of sulfur in the oil, and our fuels these days we have to take the sulfur out of the oil in order to produce our fuels, because otherwise we'd have lots of sulfur oxide emissions, and all that sulfur that gets taken out of the fuel ends up somewhere, and so we have a lot of sulfur around, so we can use that any time. Other stuff that's maybe you may be surprised. There's titanium on this list too, and we have a lot of it. It's like the 9th most element. Nickel is quite rare on the one hand, but it's much more common, especially in production, than something like cobalt. The other thing you might want to know about elements. By the way, it's really hard to find a good periodic table that shows the right numbers, and the only one, and is free to use. And the only good one I found was a Japanese one. I'm sorry, but it shows the right numbers. That's important. One of the important things, if you want to have a battery that is light and has a lot of power, is the weight. These little numbers that nobody cares about down here. That's one of the most important numbers, because that's how much the atom weighs. Chemical reactions only work with the outer electrons in the outer shell, and the energies of these electrons in the outer shell are kind of similar. It's always like a few electron volts. It doesn't differ too much. I mean, it's like, okay, it can be 1, it can be 5, but it's not like one has 5 and the other has 500. On the other hand here, everything goes from 1 hydrogen to something like lead, which has 207. So the differences are quite huge. So when you have a lead battery, you already know it cannot have a heck of a lot of capacity, simply because the lead atoms in there are very heavy. Same goes for something like cadmium. Nickel, on the other hand, is a lot better already. I mean, you're around 60. Nickel, cobalt, manganese, iron, that stuff is around 60. And on the one hand, it's quite heavy. On the other hand, it's much lighter than the stuff we had before. Um, so when people were looking for high-performing batteries, they were looking in this corner up there. Obviously, hydrogen is the lightest atom of them all. And if you just want to burn hydrogen, you get a lot of energy out of it. On the other hand, it's hydrogen. It's a gas. It's really hard to contain into anything. And so for a battery, it's not the first choice. So what's the next best option? You may have noticed I took the noble gases and anything below fluoride out of this one just so it looks a bit nicer. But helium, no, you cannot make a battery out of helium. So they were looking at lithium. Lithium is fairly light. You see it has a weight of 7. That's 7 grams per mole. And if you want to make a battery that has the highest possible performance, it's obviously lithium. Sodium has very similar chemical characteristics. That's why we have a periodic table. Everything that's on top in one column has kind of similar chemical behavior. So sodium will play a role a bit later. But as you can see, sodium is about 3 times as heavy as lithium. And so the first choice when you look at a new battery that you might want to invent will be lithium and not sodium. And that's what was done. Of course, this year we had Nobel Prize finally for John B. Goodenough at the age of 97 years. By the way, he's still a researcher. He still researches in batteries, lithium batteries, and also sodium batteries. And this was a revolution. It was really the big breakthrough. If you ever look at, I mean, there's so many articles that I try not to write that say, yeah, this next super battery is just around the corner. On one hand, developing this thing took from the 1970s until the 90s. Just to make it work properly and commercialize it. The first ones were offered in around 1991. But it improved, and improved quite a lot since then. As you can see, it's almost 2.5 times the capacity in the last 30 years. Unfortunately, there's a lot of people who write articles saying, yeah, okay, we can get 5 times or 10 times the capacity within the next 5 or 10 years. By the way, these kinds of articles and announcements have been made ever since batteries were around. I mean, you can actually find articles in the around 1900 that said the same thing, like, yeah, okay, 10 times as much in the next 10 years. Well, let's put it that way. 100 years later, we had about 10 times as much. So that's about how long it takes. But it's actually not bad. And we are really quite good, especially in the last 20, 30 years. Improvements have been quite good. Main problem with this thing, okay, maybe I should say how it works. There was actually another talk that explained how this thing works, so I will be quite brief. You have a material with lithium in here. That's a cathode. And when you charge it, put a negative charge in here, and the positive ions go over here and are stored. In this case, and that was the first kind of battery ever was around, was in carbon. Actually, they used coke, I think. These days, we use graphite, and graphite is we more or less maxed this one out. If you remember this table, storing it in graphite has a problem. You see up there carbon. Carbon has a weight of 12. And when you store lithium in these layers, you need about 6 carbon atoms to store 1 lithium atom. And the carbon atoms together, 6 carbon atoms, have a weight of 72. The lithium atom has a weight of 7, so the carbon is about 10 times as heavy as the lithium. So obviously, this is not ideal. But it took a long time just to max this out. These days, I think they're at around 90% or so of the theoretical capacity. So if you want to do something with graphite, you cannot improve this much more. On the other hand, here, this one says metal cobalt. And this is because lithium cobalt oxide was a material of choice from the beginning in lithium batteries. It was pure cobalt oxide. This too has changed. Damn it. Okay, this will change and we will see it later. Lithium. Where's lithium coming from? This year, I was always sure that most of the lithium is coming from Chile, and it's not too bad. I wasn't wrong, but actually this changed in the last 2 years. These days, most of the lithium is coming from Australia. And what changed is that lithium used to be mined simply by pumping water into the ground, into salt layers where you had a lot of lithium salts, pumping the water up, evaporating it, concentrating it, and extracting the lithium from that. There are some spots where this is possible, and this is actually quite easy and also quite cheap. But that's limited, and we've pretty much run up to the limit. In Australia, what they're doing is mining ores. Ores like this one here. Spodumene, this is a lithium aluminium silicate. And in theory, they could contain about, the ores themselves could contain about 6.8% of lithium by weight. No, that's lithium oxide, so it's a bit, it's about half that, so about 3 to 4% of lithium. But typically, you will get maybe 1% of lithium by weight. And that's just for the ore. You have to get to the ore itself. And when you mine something, you not only get the ore itself, but also other stuff. So actually, you need to mine maybe about 1,000 tons of stuff in order to get 1 ton of lithium. And that sort of thing is done on a large scale in Australia. And that's where, as you can see, that's where it's coming from. And most of that is, by the way, from Chinese firms, because most of the batteries are made in China. Cobalt. Cobalt is a huge problem. A problem, for one thing, because we don't have too much of it. As you have seen, it's about as much as lithium, and you need a lot more cobalt in your battery than you need of lithium, simply because, I mean, it's the same number of atoms. You know, if you had lithium cobalt oxide, you need 1 lithium atom and you need 1 cobalt atom. But the problem is a cobalt atom is about 10 times as heavy as a lithium atom, so you need a lot more cobalt than you need lithium. And so we first ran into the problem of running out of cobalt. Cobalt is mostly mined in the Congo. You will have seen a lot of pictures like this one and much worse ones also. And about a quarter of the cobalt is mined in the Congo. No, sorry. 2/3 of all the cobalt is mined in the Congo, and 1/4, it depends. It depends on the current economic conditions. Something between 10% and 1/4 of all the cobalt in Congo is mined by small-scale farms, like small-scale mines like this. But most of it, also mostly by Chinese companies, or at least to a large part by Chinese companies, mined in something like this. If you go and look for pictures of cobalt mines that are free to use, you only find these. So I have a placeholder. This is actually a copper mine. I'm sorry. But I really didn't find a free picture of a large-scale cobalt mine anywhere. But the main problem is really the Democratic Republic of Congo is a war-torn poor country, and it's really worth reading up on the history of this country. And that's the problem. The problem is not cobalt. Cobalt is just it's just an element somewhere in the table. Don't blame the cobalt. Blame the social situation in this country. And aside from that, we still have limited reserves. So there are many good reasons not to have cobalt, or to at least reduce the amount of cobalt you can have. And this is what has been done. Also because cobalt's getting expensive, the more demand there is for cobalt, the higher the prices get. And when demand outstrips the supply, prices just skyrocket. So people had to find alternatives, and they did. These days, modern lithium-ion batteries use something like nickel-manganese-cobalt mixtures instead of just pure cobalt. And you have numbers like 532 or 811. The 811 means 8 parts nickel, 1 part manganese, and 1 part cobalt. So today, batteries use between 1/10 and 1/3 of the amount of cobalt that they used to use. There are also other possibilities. You can use something like lithium iron phosphate. Has no cobalt in it at all, but the problem is you only get about half the capacity out of the battery. And especially when you have something like a car that you want to have as much range as possible, that's not really an option, at least for this. It has other positive properties, like it's much more robust. It cannot decompose thermally, like a lot of the cobalt-like materials can. But it's possible. Lithium sulfide. Lithium sulfide is something that everybody would really want to have. And trust me, it's not for want of trying. Because, sulfur is only an atom of sulfur is only half as heavy as an atom of cobalt. And you can have 2 lithium atoms together with 1 sulfur atom. The problem is the lithium has to somehow you have to get rid of you have to divide the lithium and the sulfur. And when you divide the lithium and the sulfur, at some point you do it in stages. At first you have like 2 lithium atoms and 1 sulfur atom, and at some point you have 1 lithium and 1 sulfur, and then you have 2 lithium and 3 sulfur, and so on. And you do it in stages. And one of these stages, unfortunately, is liquid inside of the electrolyte. And that means that your cathode is now suddenly soluble, and it begins to slowly but surely destroy itself every time you charge or discharge the battery. And this is a problem that hasn't actually been solved yet. There are companies that sell these lithium sulfide batteries, but they only have relatively short life. And the way they did it is by just putting a heck of a lot of material, a heck of a lot of lithium sulfide into the battery, so that it still destroys itself, but it takes longer until it's completely gone. The other possibility is air. Lithium air batteries are also one of the dreams that everybody wants to have, and lots of people are trying. This actually works almost like a fuel cell, except with lithium on one side instead of hydrogen, and air on the other side. The problem is that you now form an lithium oxide on one side on the cathode side of the electrolyte, and it's very hard to really maintain the integrity of this whole thing. And especially, it works in very thin layers, but if you want to have a thick layer, and you would need a thick layer in order to actually exploit this, because, remember, what you have here is just lithium on one side, only lithium atoms, and nothing else on the other side. That would be great. That would be perfect. It would be like 2 kilowatt hours per kilogram of battery. That would be really nice. But it really doesn't work. You only get it in very thin layers, and then you have a, relatively speaking, thick layer of electrolyte between that. And so long as the electrolytes that you need are so thick that they make up more weight of the battery than the actual lithium you're shoveling back and forth, the actual capacity is still worse than what we have today. And you also have to make sure you can cycle this without losing any of the lithium on the air side. And it's a bit of a mess. It's a bit of a problem, and nobody has solved this yet. Yeah. Okay, I used to have the other slide before that. That's why. Yeah, lithium is just as rare as cobalt, and we have to replace this at some point, maybe as well, because lithium supply is limited, and we have to get like 20 times as much batteries into production as we have currently. Okay, anode materials. Right now we have talked about one side of the battery, now it's the other side. You remember the graphite with the 6 carbon atoms. Well, you can improve this. If you don't use graphite, you can use graphene or graphite or some nanotubes or multi-volt nanotubes. Unicorns might help. Maybe unicorns can make those cheaper. But no, right now you can find a lot of papers and a lot of science being done with graphene and nanotubes and so on, and it works. It actually does work. The problem is this is about as expensive as gold. Maybe not quite, but almost, and it's not useful for batteries right now. Maybe someday somebody gets to make those on the cheap, and then it's an option. Silicon and phosphorus could help as well. It could improve upon the graphene, on the graphite, have much higher capacities, because especially with silicon forms an alloy with lithium, and you get much better ratios, and so you can get much higher capacity. The problem is when you form such an alloy, what you get is much bigger. The electrode just gets much bigger. It gets 4 times as big as it was before, and this puts a lot of stress on the material, and it starts to crack. And basically, every time you use the battery again, it destroys itself. That's not helpful. Maybe. I mean, there are tricks. Some people make lithium like the wafers we use in chips, and make them very small, and you have very small structures that can store the lithium inside of them without cracking, because they are very small. But they never talk about price for some reason. I don't know why. I think it might be too expensive. Okay. The other thing you can do, and there is active research, and it's quite promising actually, is pure lithium. Just nothing. The reason why nothing hasn't been done before is the lithium. When you grow lithium by electrochemical means, you just put one atom onto whatever lithium is already there, and you do it by an electric field, and all the atoms go wherever there is the strongest electric field. The problem is the strongest electric field is wherever there's like a little peak, a little bit of like a needle, the point of the needle or something like that, and that's where they go. So what you get is dendrites, that is like small needle-like projections that grow ever more and ever faster, and that has prevented use of just pure lithium anodes, even though that would essentially halve the weight of the battery. That's why people want to use it. You would just cut the battery in the weight of the battery in half, and get about twice the capacity. What you need is solid electrolytes, because you see, right now the electrolyte, that's the stuff that's between the cathode and the anode, is a liquid, and that's why these dendrites can form. When the electrolyte is solid, like in the sodium-sulfur battery, like the hot stuff that we had before from Ford, there's already something solid in between there, and so nothing can grow through it, at least if it's solid enough. And people are working on this. They have made some advances. one of the problems is it's still a bit too heavy. The electrolyte's a bit too thick and too heavy, and it's a fairly slow process. You have, I mean, after all, it's no longer a liquid. You have to get the ions through through a solid material. So the other problem, yeah, as I said, I switched 2 slides around, so now we talk about sodium. Sodium can replace lithium. As I already said, sodium is about 3 times as heavy as lithium, so it's not perfect. But on the other hand, since lithium currently only makes up about maybe 3 to 5% of the whole of the weight of the total battery, switching to something that's 3 times as heavy isn't quite so bad. One of the problems is that there's a lot less development that has been done on using sodium instead of lithium, simply because people started using lithium because it was the best performing material and there was plenty of lithium around. Why not? I mean, especially in the 1990s, lithium was mostly used as a grease or as I don't know, like for colors. I think they didn't use a lot of it. So there was plenty. There was a lot of supply of it, and so why waste your work on sodium when you have something that works and something that is always going to get you better performance? So sodium will always be the second best in performance, and so people didn't really start development on it. They have started development on it in the last couple of years, maybe this decade. You get a lot of more papers if you search online in scholargoogle.com. If you didn't know that page, it helps a lot to find scientific material. You find a lot more work on this. And there are even some companies that are selling them more like as trials than as actual products, but at least it's something, and they have capacities of 140 watt-hours per kilogram, and that's similar to what we had in the year 2000 in lithium-ion batteries. So development lags behind about 20 years, roughly. And they still don't have this same kind of durability and cycle life that we expect today. They can sustain maybe 200 or 300 cycles. These days we expect a lot more than that. All that is the result because there has been much less development in the materials overall. Sodium is very similar to lithium, but there are always some subtle changes, and it just needs to be understood. It's simply you need a lot of scientists on benches and in front of their computers crunching data, doing experiments just to find out what we don't understand and what we do wrong. Yeah. The other problem is, I mean, batteries are great for stuff like this microphone or my smartphone or maybe a car. But at some point, you want to store more energy. And batteries won't cut it. At least not lithium batteries. Sodium, maybe. Sodium, there's huge amounts of sodium. We're not going to run out of sodium, trust me. But you still have, when you have a battery, you have to purify the materials, you have to assemble them, there's a lot of processing going on, and that's a problem when you want to have something that's really big, something that can store a huge amount of energy, like we need for storing, something like the grid level energy. I've given you. I mean, if you read about it in the news or in articles, you will usually find something like this. This is from June. This is perfect for solar energy. As you can see, lots of solar energy. But right now, this is what we had this month. Almost no solar energy, and we had some wind, except when there's not. And we kind of need to store the wind the wind energy in order to have energy when we need it. With solar energy, it's much easier. But the trouble is, we're here at 91 degrees north, and at 91 degrees north, here in Leipzig, for example, it kind of looks like this. In winter, it's cold, and it's cold because we don't get a lot of solar energy right here. It's very different when you're somewhere in California or even in Spain. I mean, Spain is already a few degrees further south, and they get a lot more sun in winter, as you can tell from the temperatures, actually. And so you can rely much more on the cycle of the solar energy, like every 24 hours and so on. But here we need much more storage. We need to be able to store energy from times like these and use it in times like these when you don't get any. And now we're talking about, I mean, we need 80, I think, yeah, I have it on this slide. I mean, the amounts we need is huge. 40 gigawatt hours. By the way, 150 gigawatt hours is the worldwide production of lithium-ion batteries. Okay, 40 gigawatt hours in Germany is enough for 30 minutes of power supply. Let's say we really need a heck of a lot. One of the large-scale, what we consider large-scale storage possibilities is pumped storage. And problem here is physics. Physics like this. E is mgh. M is the amount of water, the mass of the water. H is the height to which you pump it. And G is the gravity. We've maxed out gravity. Actually, in this solar system, you will not find a solid surface that has more gravity than ours. So we cannot optimize that further. I'm sorry. Height, if you get something that's better than this, I mean, this is not 360 meters, but I assumed here 360 meters for one simple reason. It's easy to do the math on. Then you need 1 ton of water to store 1 kilowatt hour. And 1 kilowatt hour for one ton of material, that's a heck of a lot. And that's why these are almost always huge and don't store a lot of energy. And the total storage is something on the order of 40 gigawatt hours in Germany. There have been other proposals like compressed air storage. What you do is here in Germany there used to be a sea here around Germany, and a lot of the salt water from the oceans evaporated and left behind a lot of salt. And we get these salt domes. And so what you can do is you can make holes inside the salt simply by pumping water down into the salt and dissolving the salt. And then you have a huge hole in the ground, except you cannot see it from the surface. Here it's a bit better than the pumped storage. When you do the math on it, you can get about 3 kilowatt hours per ton of salt that you've removed from the ground. This assumes 70 bar. You can have, if you go deeper into the ground, you can have higher pressure. You can have more than this, but it's kind of limited. And also, you have a hole in the ground, and this hole will collapse sooner or later. I mean, these holes are stable for us. They're stable for centuries, maybe thousands of years. But eventually, they will collapse. Something will go down. And sometimes, when people don't pay enough attention when we're making these holes, it actually happens. And you can find accidents where this actually happened. Okay, how does this work? Well, it's very simple. You pump the air in, and you take it out. You let it blow through a turbine. It's almost like wind energy, except for really good turbine, and you get energy from it. Problem is, when you compress the air, it gets really hot, and then you store it, and it gets cold, and then you let it out, and you decompress it, and when you decompress air, it gets even colder. And that's how you lose a lot of energy. And so what is done, there's one of these is in Germany, actually. There's one in Germany and one in the US. And what they do here is they burn natural gas in order to make up for the heat that was lost. It actually makes the the power plant itself more efficient, but yeah, it's not exactly renewable. What people actually want to do is store the heat. So as I said, when you compress the air, it gets hot, and then you want to store the heat. And when you decompress it, you put the heat into the decompressed air and heat it up again, and it gets much more efficient. So instead of 45%, you get up to about 70%. Oh, damn it. OK, I was way too slow. The way you can store this heat is something like this. Thermal storage, there's a lot of thermal storage using liquid salt. Liquid salt is not terribly efficient at that task, especially because not very high temperatures. But you can actually use stones, like volcanic rock. I think Siemens is building something like this. And what they use is basalt rocks, like about this big. I mean, couple of centimeters. I mean, like the pebbles you can see here. It's a very, very, very slow, very small storage, thermal storage. You want to build these things big. And when you build them really big, they're really efficient. Because, it's a matter of geometry. When you have something like a cube, and it's 1 meter on each side, and you make it 2 times as big, it's 2 times as wide, 2 times as long, 2 times as high. It has 8 times the volume, but only 4 times the surface area. And when you and the problem is, you lose heat through the surface area. So when you have 8 times the volume and 4 times the surface area, it means that your heat losses are only half as big. And that's not actually enough, because when you take something like this and you build it 2 times as big, you will also make these parts 2 times as big, and that's the insulation. And when you make the insulation 2 times as big, you also reduce the losses by a factor of 2. So when you build something like this, really, really, really seriously big, you have very small losses. You have losses for small ones. You get losses of about 1% per day, and when you build them like 1,000 times as big, you can, in theory, get 1/10 of that. In theory, you could store heat for weeks or even months in these, and you need. I thought I had this memorized, but you need, I think, about 10,000 tons in order to store 1 gigawatt hour of electrical energy, because you can actually use this to store electrical energy. Yeah, okay, I'm sorry. Everybody enthusiastic about hydrogen, I will not be talking about hydrogen because I'm running out of time. And yeah. Big thing here is it has really cheap raw materials, simple stones, and capacity is fairly high. You get about 30 to 60 watt hours per kilogram if you try to take the heat, because you can heat these up to about 800 degrees Celsius and run them through a common turbine, like the turbines you have in a coal-powered power plant. And you get an efficiency of 45% out of this. That's not very good. Especially not compared to a battery, where you would get efficiencies on the order of 80% or 90%. It kind of depends on how fast you charge. So if you have a Tesla supercharger, you have much less efficient batteries than if you take it slow, charge it slowly. But for something as simple as this, 45% is pretty good, especially because you can scale it up into the gigawatt-hour range and even tens of gigawatt-hour range, which is kind of like what we need. Yeah, and all you need is stones, fairly huge amounts of stones. The reason why I think this is a pretty good idea, even though it's not perfect, as I said, 45% you waste half the energy, is because hydrogen is even worse. Yeah, okay, I tried to do this in 2 minutes. I'm sorry. It's going to be very fast. Okay, hydrogen, in theory, it sounds great. You split water into hydrogen and oxygen. You use the hydrogen to get energy, and you have really great density of energy. 39 kilowatt hours per kilogram is really great. You have theoretical efficiencies of 83%, and yeah, that sounds great, but in practice, well, the problem is the efficiencies are usually related to the lower heating value, which is not the higher heating values. So there's a fudge factor of about 18% in the efficiency, or actually 10% in the efficiencies when you get to the real efficiencies. So when you have, when they say, okay, 60% efficiency for the electrolysis, no, when they say 70% efficiency for the electrolysis, the reality is more like 60%. And for the fuel cells, it's more like 50% and 60%. And the reality is, when you take all the losses into account, including the storage, you get about 1/3, and very often much less than 30% of the energy out of it than you put into it.
I'm sorry.
That's a big problem. Okay.
You ran out of
I'm
time.
sorry, I've run out of time. Okay.
Thank him for his great effort. And
Yeah. I couldn't see I really couldn't see the clock until just now.
okay.
I
Thank
think
you.
it was switched off on at first. That's why I kept looking at my watch. Sorry.